Here we go. So you got this little package there the other day. It's entitled "What Do You Know Already?" You'll remember, those of you that were here, we spent, I don't know, maybe 20 minutes or so. We texted some answers up to the screen. The questions were: what is a scientific model? What is a scientific law? And what is a scientific theory? And those were strictly your opinion. I didn't say yes, that's right, or no, you're wrong, did I? Okay, that's fine. So, and then I gave you a little bit of time to finish numbers 4 to 8, and that's when I said you need to wrap up that lab then, because I'm moving on. So, number 4, who would like to volunteer? Let me pick someone here. Logan, you look like you're bright-eyed, bushy-tailed this afternoon. No? Come on, you can answer this. How do we prove scientific theories? Okay, Aurora's going to bail you out, and it looks like Connor wanted to as well. You test them. You do experiments and you check things out, right? Exactly. Exactly. Okay. And we're going to talk a little bit more in this period about what a theory is, because I've asked you that question in number 3. Certainly, we test them out. What about number 5? Do you believe in atoms? Brett says yes. Why do you believe in atoms, Brett? That's what you've been told. That's what you've been told, but, well, first of all, you say yes. But, I mean, why? No. You mean that cartoon one where they, the coppers and the, yeah, no. But why, Ben? Why, like, how do you know it's a fact?
They make up cells.
Who are these magic they people?
It's stated in a theory.
It has been stated in a theory, that's true.
That has not been proven on yet.
The vast majority of people certainly believe in atoms. Miguel, you ever seen an atom before? Not a single one.
No.
Ben, ever seen an atom before? Yes, atoms have a chart. I set you up there, didn't I? Nicely done. Do atoms exist? Yes. We've all been told they do, right? Right from probably, about grade 5 or so. Atoms, they exist, right? But you've never seen one, have you? You ever seen an experiment to show you that they're real? Maybe we've been, it's been a big teacher joke for the last couple hundred years.
Maybe that's been the link to YouTube right there.
Maybe. Maybe. The point is, though, is that you've been told they exist. You've probably been shown lots of evidence, and it's a sort of generally accepted fact. But you've never seen one, right? Yeah. Never seen one. Okay. And you do have to be careful about just sort of listening to what people in authority always say, right? They believed Aristotle for about 2,000 years. Turned out he was wrong. We'd be a little bit farther ahead if we hadn't listened to Aristotle. We as humans. How are science and art similar and or different? Mary, I'll give you the easy one. Whoever's next gets the hard one. How are science and art different?
They're different because science is based on facts, where art gives you freedom.
Okay.
And they're similar because you have to think you start figuring out what it is.
Okay, that's a pretty good answer, really. I like that. More about the difference. If I give you an art assignment and a science assignment, what would be one big difference between the two?
Research with science. Well, depends what the art one is.
Think more about the marking part. Like, how would I mark an art assignment compared to a science assignment?
Art would be on presentation, science would be on what you know.
Would I have an answer key for a science assignment compared to an art assignment?
Yes.
So what am I getting at here, Miguel?
My teacher like I've had an
Say again? There's generally one answer that we're looking for, right? Generally one answer that we're looking for. An art one, and this is along the lines that you said, you got it right. Generally it's more of a subjective kind of thing, right? Okay. Now what about similarities? Mary said that they're similar because you have to sort of do some planning ahead of time, is that what you said? Anybody want to expand on that at all? Okay, Aurora?
They both require a lot of creativity.
Okay, I'll give you that, sure.
There's lots of ideas within both.
Yeah. Would you agree that to truly appreciate good art, you have to sort of know something about art to begin with, right? Like I could just throw up, years ago there was a painting that the Canadian government bought for like $1 million, and it was just like canvas, but the size of a door, and it was painted red. Like it looked like someone's garage door. Most Canadians said that's a bunch of junk. Why are we paying $1 million for that? The art experts said, oh, they appreciate it, right? I don't know why. I'm not an art expert. Would you agree that science, if some crazy professor dude walked in and filled the whiteboards, would you be impressed? Probably. Would you know what he was talking about? No. If he made a mistake, he was completely wrong, would you know? No. You sort of got to understand something about science to really, truly appreciate it. So there's a similarity as well. All right. I'm a bunch of touchy-feely sort of philosophical stuff, and then tomorrow we'll get into the, real physics. Some astronomers say that the universe is expanding, some say that it's shrinking, and others say it remains a constant size. This is true. How can these scientists arrive at completely different conclusions when they look at exactly the same evidence? How can they come up with different conclusions?
They can conduct an experiment.
No, they're looking at exactly the same evidence.
Same with
Are you?
I put that astronomers can associate conclusions because they all have different theories, and none of them can actually prove if they're right or wrong.
Okay, you're sniffing in the right ballpark, I think, for what I'm looking for. Would you agree that most people, when they do an experiment, they have something in mind that they think is going to happen?
Yes.
Okay. So, a prediction, right. So, when they do an experiment and they come up with evidence, they are probably looking at the evidence to do what? Prove their hypothesis, right? So, if I've got one hypothesis and someone else has a different one, they might look at the evidence and say, well, yeah, look at this. This proves my hypothesis, right? Or is evidence towards my hypothesis. And someone else might say, well, no, look at this. This means this, right? They can take the same data and they can sort of twist it for their own benefit, kind of thing, right? So you got to be cautious about that as well. All right, the last one I think is pretty easy. Can scientific theories change? Yes. And can you give me an example? Kish says yes. Scientific theories can change. Adele, let's hear from you. Can scientific theories change?
Yeah, and some more facts come up with more research.
Okay, so new things are discovered. The theory might have some, shall we say, modifications to it? Yeah? Okay, that's good. All right, before I show you the YouTube clip, on the board I have hypothesis, theory, law. Hypothesis, arrow, theory becomes law. True or false? Hands up. Make a bold statement and say, I believe that true.
My neck.
Okay? Fair number of people. And they want to say, no, that's not true. Good for you. Good for you. Huh? Yes, both? I'm sorry? It's false? Why do you think it's false? Okay, Aurora, do you want to?
Doesn't necessarily lead to a law because it could be.
Okay, so you're saying that if the theory is proven wrong, then it can't be a law. Okay. Okay. Right.
Could it be no or false because if your hypothesis is based on previous accusation?
Okay. The point that I'm trying to get at here is really what is your definition of the word theory? Okay. I'm going to show you a video here. It's about 2 minutes long. He's kind of hard to hear. I have to turn it down, otherwise it gets kind of distorted. So you have to be really quiet and you have to listen very close. Okay. He's got kind of a weird voice too. So, okay. But he might shock you. What does he mean by it's rubbish?
It's garbage.
Do theories become laws?
No.
What did he say? Theories try to do what?
Prove them.
Try to explain things, right?
Would they explain? No.
Well, laws are simply
Accepted facts.
things that we see happen. Okay? He talked about the theory of gravity, about inverse square law, blah, blah, blah. You guys don't get that. That's fine, right? Most people think the theory of gravity right? Would you say the theory of gravity is what goes up must come down? Would you call that the theory of gravity?
No.
Or the law of gravity?
Law.
Okay, probably the law, right? Because every time I throw the tennis ball up, doesn't matter how many times I do it, I can do it all day, all period. When it goes up, it comes down. The law is this is what is going to happen, and that's that. Now, explain to me why it comes down.
Because of the force pushing down.
That's a little harder to do, right? That requires a theory. It requires some data. It requires lots of explanation, maybe diagrams, all kinds of other stuff. It's giant, big giant explanation. But what goes up must come down. It's pretty simple. It's a law. Okay? Theories do not become laws because they're not like a law is not like a theory is not like a junior law. Okay? It's just not true. Let me show you one more clip here. This gentleman here, Rick Perry, was the governor of Texas. He was running for president of the United States. Listen to what he has to say. Clearly, Governor Perry wasn't listening very close in grade 11 physics class, right? No doubt when that aired on ABC News, I don't know, 3 or 4 or 5 years ago, probably thousands of science teachers across the country were cringing.
This is George. He is a good little monkey and always very curious.
All right, so is Governor Perry, is he saying true or false?
It's law.
Saying true.
He's saying true. He thinks that theories finally become laws. Simply not true. Okay? It's the definition. A theory is not an unproven law. Not true. Okay? Now, do we use that word in everyday language? Oh, it's just a theory. We do use it, right? But what we really mean is it's just another word that starts with H. Hypothesis. People have a hard time saying that, so they say theory instead. That's not the true definition. Okay? It's just a hypothesis is a guess. Do hypotheses become theories?
Yes.
Absolutely. But the next step is not a law. A law is something completely different. That's what you need to get out of this. Okay? Got it? And if you run for president or prime minister, please don't get up and say, it's just a scientific theory, because I will yell at you.
I'll do it. Just kidding.
I'll forget it works better.
All right. What I would like to do now is I'd like to go to that next page.
What is sneeze?
Fine, but you know what? I will get to the story of Clever Hands. That's it's not a really good story, but it's kind of a nice little thing. That's just there because it was a single page. Let's go to the theory.
Pardon me, what part?
Okay? The next page.
Models, theories, and
I'll
laws.
find mine here. Hard time here.
He said what?
Oh, okay. So you'll see up in the top right-hand corner there, there's a little cartoon with what's supposed to be Einstein there, and I don't know if you can read it or not, but it says E equals MA, and he's got that crossed out, and then he's got E equals MB squared. He's got that crossed out, and it says underneath, theories are not really developed this way. I have to sort of go alphabetical. All right. You're going to hear some pretty big words here and some pretty deep thoughts, okay? So just sort of sit back, grab a highlighter and a pencil, and just sort of try and soak it all in. When scientists are trying to understand a particular set of phenomena, they often make use of a model. What is a phenomenon? And it's not the song on Sesame Street. Yes, it is. Thank you, Ben. What is a phenomenon? It's hard to say that word without whistling that, isn't it? What is a phenomenon? Anybody?
It's something that happens.
Just something that happens. Just something that happens. That pretty much sums it up. Okay? So, this page right here. When scientists are trying to understand a particular set of phenomena, they often make use of a model. A model in the scientist's sense is a kind of analogy or mental image of the phenomena in terms of something we are familiar with. One example is the wave model of light. We cannot see waves of light as we can water waves, but it is valuable to think of light as if it were made up of waves because experiments on light indicate that it behaves in many respects as water waves do. So we use a water wave as a model for light. The purpose of a model is to give us a mental or visual picture, something to hold on to when we cannot see what actually is happening. Models often give us a deeper understanding. The analogy to a known system, for instance, waterways in the above example, can suggest new experiments to perform and can provide ideas about what other related phenomena might occur. So it's a way to sort of continue with the idea of this theory. No model is ever perfect, and scientists are constantly trying to refine their models or to think up new ones when old ones do not seem adequate. The atomic model of matter has gone through many refinements or changes. At one time or another, atoms were imagined to be tiny spheres with hooks on them to explain chemical bonding. Okay, so they thought like atoms were like these little balls, and they had like little hooks on them, but that's how things bonded together. Well, that's crazy talk, isn't it?
Trauma studies babies.
Should. Or as tiny billiard balls continually bouncing against each other. More recently, the planetary model of the atom visualized the atom as a nucleus with electrons revolving around. You've seen that before, right? Bohr diagram, exactly. You've got your nucleus here, right? And then you got your electrons whizzing around in pairs. You guys have drawn those before, right?
Yep.
Not true.
What?
It's not true.
I
mean, the atom, if you could zoom in and look at an atom, it wouldn't look like that.
Oh.
Oh, I
I
thought
mean, it's
you
not
said.
true.
Oh yeah, no, you've drawn them, right? Now, is it entirely not true? No. Are there certain bits of truth to it? Yeah. Yeah, okay. But this model is oversimplified and fails crucial tests, okay? As you progress in your chemistry studies, if you do, you'll find out that the Bohr model needs to be refined a little bit more. Fair enough. Why do we use it for grade 9 and 10 science tests? It's easy. It explains what kids at that age need to know, and it helps them sort of prepare for the next step, right? It's like playing t-ball to begin with, kind of thing, right? Or maybe having the net a little bit lower or mini volleyball at 5 and 6, same idea. You may wonder what the difference is between a theory and a model. Sometimes the words are used interchangeably. Usually, however, a model is fairly simple and provides structural similarity to the phenomena being studied, whereas a theory is broader, more detailed, and attempts to solve a set of problems, often with mathematical precision. So the model is just sort of the structure kind of part of it. The theory is all the notes that go along with it as well. Often, as a model is developed and modified and corresponds more closely to experiment over a wide range of phenomena, it may come to be referred to as a theory. So models could become theories, right? As sort of the notes pile up with the model, then that could become a theory. The atomic theory is an example, as is the wave theory of light. Can you think of any other models maybe that might have become theories that have changed, I'll even say in the last 100 years? Kish is pointing over here. Oh, the globe, that's great. No, I picked that one up, Kish. Explain for us, please.
People used to thought the world was flat or square.
Okay, that wasn't the one I was thinking about, but that's good.
Oh.
Okay? Yes, they thought the world was flat. In fact, if you Google up Flat Earth Society, there are still, and more than 10, a lot of people who believe the world is flat. Oh, yeah.
Are the same people who believe we have a
Pardon me?
Are the same
Yes,
people-
probably they share that saying, yeah. No, there is indeed people that think the world is. I mean, you go out, right? You go out and you look out and you go, yeah, it's flat. Like it's what you see, isn't it?
Actually, you still can't see it.
If you look at the sky, you can see the picture with the clouds.
I suppose.
Yeah, but they've taken pictures from the
Yeah.
Yeah.
outer space.
We pretty much, is it a theory that the Earth is?
No.
It's pretty much a fact.
It is a fact.
Yeah. It's not pretty much, it's 100% Connor. Oh, Connor, he feels strongly.
They've taken pictures from space.
Yeah, I know, I'm with you now.
They could be.
It could just be like a giant flat circle.
Oh, yeah.
Oh, yeah.
Giant flat circle. What I was getting at, but that's good, that was a good little discussion. What I was getting at was the idea of continental drift with the plates, you know?
That's what I.
That's a relatively new theory, right? It certainly started off as a model, and now there's more and more theory to it. They talk about the volcanic activity, right? The lava is pushing the plates apart, and there's all sorts of Phil's books kind of thing, right? So that's certainly a model that's become a theory that has evolved, changed in the last Flat Earth Society, yeah. Yes, I'm sure you'll derive hours and hours of enjoyment from that. Here we go. All right. Models can be very helpful and they often lead to important theories. But it's important not to confuse a model or theory with the real system or the phenomena themselves. Obviously, this is not a real world. It's just made out of cardboard. Don't confuse that. Okay? Now, here's the definition of a law. Scientists give the title law to certain concise but general statements about how nature behaves. For example, momentum is conserved. That's called the law of conservation of momentum. There's other conservation laws. Law of conservation of energy and law of conservation of mass. Exactly. Those are laws. Matter must be conserved. That's the law. Do it. Right? It's the law. It just happens. It's just a simple statement. That's the way it is. No explanation. This is what happens. Okay? Sometimes the statement takes the form of a relationship or equation between quantities, such as Einstein's famous equation, E equals mc squared, right? That is a law. Here's another one, Newton's law, F equals ma. It's written as an equation. Almost all the equations could be considered law. Boyle's law, the pressure laws, Ohm's law, Snell's law. If only there were a Bennett's law. Only there were, Kish. If there were a Bennett's law, what would it be? Yeah. To be called a law, a statement must be found experimentally valid over a wide range of observed phenomena. In other words, you must have done it several times and gotten the same result over and over again, right? And someone else must have done it several times and gotten the same result over and over again. In a sense, the law brings a unity to many observations. For less general statements, the term principle is used, such as Archimedes' principle. Where to draw the line between laws and principles is, of course, arbitrary, and there's not always complete consistency. Let me demonstrate. I will demonstrate the principle of the pink ruler. When you throw a pink ruler up, it comes down. The principle of the black pen is that when you throw the black pen up, it comes back down. There's also the principle of the green highlighter. When you throw it up, it comes back down. It's so funny. Now, you could summarize that off with a law that says, you know what, it doesn't matter whether it's a pink ruler, a black pen, or a green highlighter. Everything you throw up must come back down. That's a law. Okay? Principles are very sort of specific. Laws are a little bit more sort of generalized. No.
Okay.
I know this is not my favorite class to teach. It's kind of boring.
Yep.
This particular lesson. I understand that. I gotta get through it.
Okay.
Stick with me. Scientific laws are different from political laws in that the latter are prescriptive. What does the latter mean? Anybody know? I mean, when someone says the former and the latter, what does that mean? The first one is the former, the second one is the latter. Okay, so scientific laws is the former, political laws are the latter. So political laws are prescriptive. If you go to the doctor and you get a prescription, he says, here's some medicine you should take. Pardon me? No, it's a prescription. Prescription. It's not a prescription.
What?
Prescription. Prescription. It's not per, it's prescription. P-R-E. Okay, so Bray, that's your driver's license? Okay. What happens? What do you do when you get to a red light? What happens if you don't?
You could die. We could.
Will the universe collapse because Bray is not stopping at a red light? Yes.
No.
His universe might, but so a political law like that, one that man has created, is what you should do. You should stop at red lights. Whereas a law of nature doesn't tell you what you should do. A law of nature says what will happen. What you do.
And the yellow light to speed up.
What you do. What actually happens. What will happen. Okay? So they are not prescriptive. Scientific laws are descriptive. Descriptive. They say what will happen. They do not say how nature should behave, but rather describe how nature does behave. Flip the page, you guys that are following along. Okay? As with theories, laws cannot be tested in the infinite variety of cases possible. Guys, I need you to listen to this. Okay? So we cannot be sure that any law is absolutely true. We use the term law when its validity has been tested over a wide range of cases and when any limitations in the range of validity are clearly understood. Even then, as new information comes in, certain laws may have to be modified or discarded, or they might be said to be only true in certain situations. Scientists normally do their work as if the accepted laws and theories were true, but they are obliged to keep an open mind in case new information should alter the validity of any given law or theory. Maybe one day when I throw the tennis ball up in the air, it won't come down. That will be kind of, perhaps, yes. Laws have certain limitations. All right. Now, I hate to tell you this, but we're going to go on to the next one, because I really do need to sort of give you an idea of what a theory is, okay? Hang in here. You're going to get a chance to do them at the end. Hang in here. Okay, hang in here. I got a couple more things I have to talk about. Models, laws, and theories. Science is more than just a collection of facts and observations. Models, laws, theories, and evidence all play an important role in an understanding of the nature of science. A scientific model is, and here's the good definition of scientific model, conceptual representation, an idea in your head that stands for and helps explain other things. A model can be physical, a real thing like a globe, imagined in your brain, or a mathematical number and formula. Okay, even F equals MA could probably be considered to be a model. In science, we develop models that have explanatory and predictive powers, like the model of the universe, and we test these models in the world around us. If our model predicts our observations, we accept the model as a valid description of our world. If we go out, right, and we go all the way around the world and we don't fall off the edge, well, then that kind of proves that the model is true, the round globe thing. Okay? If our model predicts our observations, we accept the model as a valid description. However, if our model encounters discrepant events and fails to provide adequate explanations, we begin to modify our model or search for an entirely different model. Let me give you an example. I'm going to model Matthew Kish. Why won't this let me do new
You
pages?
broke it, that's why.
I'll just have to go all on one big page here. I'm going to write down a model of Matt Kish.
I have 2 T's.
I spelled it wrong. What that is a discrepant event.
Whoa.
What's a discrepancy? A mistake, an error, right? So what do we do when we make a mistake?
Fix
We
it.
fix it. Okay? So the word discrepant means a mistake. Okay? However, if our model encounters discrepant events and fails to provide adequate explanations, we begin to modify our model or search for an entirely different model. Now, a more complicated system or complicated example is the model of the solar system, not the globe, solar system. At one time, it was thought that the sun revolved around the Earth, and this geocentric model of the universe was considered to be a true representation for many centuries. It was passed down for years and years and years that what was at the center? The Earth was at the center, right? And all the planets and the suns revolved around it, right? Now, the model encountered a discrepant event when the retrograde motion of the planets did not exactly fit the epicycles of the geocentric model. What? Exactly. Mr. Bennett, you're speaking Chinese all of a sudden. What the heck are you talking about? Retrograde motion. Okay, grade 9 science, you guys did the astronomy, right? Do you know how that the planet... No?
Never did it.
Never.
That's too bad, because you would learn that retrograde motion means that the planets do this. So as they travel around,
They'll spin around.
they sort of do a loop-de-loop in the sky.
Spinning inside their spin.
Yeah. Okay. So some scientists, some philosophers saw this, but no one ever wanted to question, right?
Spinning.
But it turns out that that's because we are traveling around the sun, right? The Earth's traveling around the sun, and that's what causes this retrograde, this backup loop-de-loop kind of motion. Who came along and said, you know what, let's put not the Earth at the center, let's put the sun at the center. And when they started doing the modeling for that, guess what happened to the retrograde motion? Disappeared. And everything suddenly made sense. Okay? Everything started to make
Why would they
sense.
think the Earth is the center to live on it?
Yes. Same reason why people believe in the flat Earth sector, right? Yeah. People believe that, Connor, for thousands and thousands of years.
But how, because when you go to fly with China and
Yeah.
Asia. We go here, and you go like that way. You don't go east, you go west.
Yeah.
How would that work then?
And are you talking about the flat Earth thing?
Yeah.
Oh, yeah, it would, right? I mean, there's all kinds of evidence that proves that the Earth is round.
So if
They just choose not to believe it. They're basically doing this. La 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 la.
I believe that other times flat too.
I don't know. They might not even believe it on the planet. For all I know. Okay. So, a new model, the Copernican Sun-centered model, provided a simple explanation of the movement of the planet, and it predicted the phases on Venus. What they're referring to there is, you know how you have like a quarter moon, half moon, three-quarter moon? They predicted that would happen on Venus, and a little bit later when telescopes were developed, they realized, oh, hey, that is true. The model must be correct.
Right.
Well, it certainly adds to the truthness of it, right? The correct truthfulness. Thank you. Observations can be used to test models, both externally or by thought experiments, as we rethink and apply our model to new and sometimes discrepant situations. Our observations can lead us to identify regularities and patterns in nature. Why am I yelling?
Because it's important. It's called a test.
We call these regularities and patterns scientific laws.
there's an vagina.
A law is a regularity of pattern, right? It's something that we always observe to be true.
No, you can
For example, a simple scientific law would be what goes up must come down. We can also deduce laws given a certain set of conditions. And here I'm going to slip into Chinese again. For example, if light is a wave, we can geometrically show that the ratio of the sines of the angles of incidence and refraction is a constant.
What?
That's called Snell's law.
What's Snell's?
It's the ratio of the sines of the angles of
So
incidence
that's
and
really
refraction is
fast.
constant.
I really don't
You're
understand.
like,
You don't have to.
Oh, okay, good.
You don't have to.
Then what you say?
yeah.
Yeah, it's kind of fun to say fast. We can often represent laws as mathematical relationships. Snell's law, Ohm's law, Charles' law, Newton's laws.
Slow down.
All of them.
Who's Ohm?
Ohm had a lot of resistance to his laws. Thank you, Miguel.
Ohm.
It's in electricity.
Contrary to popular belief, yeah, explain to him later. Contrary to popular belief, laws are not absolute and are often constrained to certain conditions. Ohm's law is valid only for some materials, and our pressure laws are constrained by temperature. Even Newton's laws are valid only in inertial frames of reference. More Chinese, I don't understand. Don't worry about it. This is what's important. Scientific theories form explanatory systems for phenomena and their corresponding laws, and may include presuppositions, models, facts, and laws. What's a presupposition? Lots of big words.
Presume.
Which we might refer to as an assumption, right? Okay, an assumption. For example, Einstein's theories presuppose or assume that the speed of light is constant in all frames of reference. In other words, you can't go any faster than the speed of light. That's the assumption.
Yeah.
Okay? In Einstein's world, Newton's laws, such as F equals ma, hold only for objects that are moving much more slowly than the speed of light. I know I'm boring. Hang in there. I'm almost done, Katie. I know. I know. If I was sitting where you were, I'd be going. I know.
You have another page.
I'm going to skip part of that. Don't worry.
Okay.
The last paragraph is important, so wake up.
Okay.
We must be very careful how we use the term theory. You don't want to end up sounding like that guy. Second guy. Not the first one. In everyday usage, the word theory often refers to an idea that is not proven. It's partially true that some theories, like many cosmological theories, are speculative ideas and based on little evidence. Additionally, children often hold simple or naive theories about why things float or why the sky is blue. Hypotheses or proposed solutions are also often speculative, and we often seek to build support for them through prediction and observations. However, other theories, like theories of radiation, metabolism, chemical bonding, have considerable evidential supports. It's impossible to prove our theories for every possible case, but robust theories explain a great deal, and we sometimes literally bet our lives on them. When Connor flies to Asia, golf, he's betting his life on some theories about flight, certainly. If the plane doesn't stay up, that's a problem, isn't it, Connor?
Yeah.
At least we're crashing to water. It's not scary.
That's what you say.
Yeah, but if you're in water, you're in the middle of nowhere.
Yeah.
Well,
And then where you say,
And that's a two-stroke penalty. Therefore, scientific theories lie along the spectrum from speculative hypothesis to robust explanatory systems. And I'm going to explain that right away. In science education, we often use early models or theories that are adequate for a less sophisticated understanding of a scientific concept. For example, Bohr's model of the atom explains all the phenomena one might expect or might examine in an introductory chemistry program. More progressive theories require more expensive background. Last paragraph, and I promise I'll quit. While it's important that our understanding of the nature of science is embedded in the context, that the world is rational and can be understood, we never really know if we have achieved the most rational or most correct explanation. In science, the truth is elusive, just like X-Files, but our beliefs must extend far beyond individual opinions. In science, we insist on an evidential argument. I want you to do one last thing for me. At the bottom of the first page, I want you to write the following thing. I'm going to erase this. Can I erase? Let me erase. I don't care where you write it down. Write it on one of those
Why
two
don't you
pages.
do the big circle thing in the middle?
Yeah, you know what? I never learned that.
Do these pages. No, it
Is it something really long?
No.
no.
All right. So theories lie along what we call a spectrum. Anybody know what a spectrum is?
A line.
Kind of a scale, like a scale of 1 to 10, right? Kind of thing. It's not like left or right. Left or right, there's no spectrum. It's either this way or left or right, right? There's no sort of in between, right? Temperature would be like a spectrum. Kind of things would be cold, really cold, super cold, really hot, right? Okay. So theories. What's a speculative theory? Well, that's generally a hypothesis or guess. And there is little evidence, very little evidence in a speculative theory. Very little evidence. Some smart guy says, you know what? I think maybe it's like this. And then they go off and they do some experiments, right? Okay? And the more experiments they do, they further that theory moves along the spectrum. And eventually, enough evidence is out there, and then other scientists say, you know what, you're right, Ben. That is probably right. I'm going to try that experiment too. And then they get the same results, and more people do it, and eventually there is lots of evidence, and we now say that the theory is robust. Now, the theory of climate change is not very old, relatively new. I certainly don't remember a lot of talk of it when I was your age. We heard about hole in the ozone and that kind of stuff, but they never really talked about climate change. So it's really 25 years, so 25, 30 years, right? Is there little evidence, or is there more and more evidence every day?
I lost it.
That's okay. I'll put up the other one from this
You
morning.
told me for a sec.
It's okay. It's okay, don't worry about it. There is more and more evidence every day towards climate change, right? There are some people that still believe it's speculation, right? Is it a theory?
Yes.
Yes. And eventually, well, it might never get past somewhere here, right?
Yeah.
They might say, you know what, all our thinking is wrong. And like the vast majority of scientists might agree that, right? But on the other hand, the vast majority of scientists might say, you know what, yeah. Okay. It will never become a law of climate change. It will just become a theory, robust theory. Okay, and it doesn't mean that it's not proven. Oh, is a robust theory proven?
No.
No, it just means that it's generally accepted as true. Okay, there's always room for, yes, there might be something in the future that we've discovered, right? Okay, you need to know that. You need to know the difference between a speculative theory, little evidence, and a robust theory, lots of evidence. And now I will stop talking.
That was a good question.